And now Tom Speth from the Office of Research and Development will help moderate the webinar and introduce the speakers.
Okay, great. Thanks, Anna. Can you hear me?
I can, yes.
Okay, great. Thank you very much. Welcome to EPA's monthly webinar series for small systems. Today's topic is treatment and control for manganese and iron. Before we start, a little bit of housekeeping duties. So at the bottom of the slide is the webinar support phone number. If you are having webinar problems, you can call that number and for help. Also, the schedule and recordings of this webinar can be found on the website below, down here at the very bottom. So you can find it there. Also, we are very glad to offer a certificate for 1 continuing education contact hour for viewing this webinar. So the requirements of them are listed here on the second slide. So you must be registered for a live webinar or be in a room with someone who's registered. You must attend for 60 minutes. If in a room with others, the names of the people not logged in to the system must be provided by the person who is logged in, and send the names to that email address listed under number 3. Also, finally, if you did not request the credit at registration, you can send an email request to that email, the same email, under number 4, or respond to your registration confirmation email. So the certificates, one note, of course, is that the certificates cannot be provided for viewing the webinar recordings, but only for this live presentation, which will last an hour for both speakers. And then if we have questions, we sometimes run an extra half an hour answering questions. So with that, if you have questions for the speakers during the talks, we encourage you to go to the question box in the dialog box on the screen. So find the questions box and type in your questions, and we like it when you put them in while the speaker's presenting, because we can organize them and get them ready for the question and answer period. So that would be great. Also, if you're interested in downloading the slides for today's talks, you can find them in the handout box in that same dialog box on your screen. And again, if you missed the poll question that was just up, and you have more than one person in your room, please type that number into the questions box. This will help us document how many people are listening to the webinar, and the attendance number helps us justify continuing this webinar series. And if you have any anecdotal stories about how the webinar series has helped you, we're always happy to hear those. And again, it helps us justify the webinar series. So with that, we'll go right into our first speaker. So our first speaker is Lili Wang. She's an environmental engineer and team lead for EPA's Office of Groundwater and Drinking Water in Washington, D.C. She has 20 years of combined experience in drinking water research, regulations, and policies. Prior to joining EPA in 2011, Lili had performed or supervised numerous studies to evaluate the removal of contaminants from groundwater and drinking water through conventional and advanced treatment processes. In particular, she served as Deputy Program Manager for EPA's Arsenic Demonstration Program from 2003 to 2010. Lili has a BS in Environmental Engineering from Tsinghua University in China and an MS and MBA from Ohio State University. And with that, I'll hand the podium to Lili.
Okay, great. Can you hear me, Anna?
Yes, I can.
Okay, well, thank you very much for the introduction, Tom, and also thank you for the opportunity to speak at this webinar. Congratulations on the successful Small Systems workshop last week. I know there were a lot of good talks, and I looked at the slides and I saw some good talks on the iron and manganese removal given at the workshop. And so what I'm going to present today is some case studies from the arsenic demonstration program to give you an idea of how some of the optimization strategies talked about last week can be implemented in the field. And this is the work I did before I joined EPA in 2011. So I start off with some background information and the design considerations for how to address ammonia and TOC in the water. And then I will talk about some bench scale tests and a year-long full-scale system performance evaluation study at a site in Illinois. And then I will finish up with some conclusions. So some of you may have heard about this EPA arsenic demonstration program from the previous webinars. It included 50 sites in 26 states, and it was initiated shortly after EPA lowered the arsenic standard from 50 to 10 microgram per liter in 2001. And the program took about 8 years to complete from 2003 to 2011. And the purpose of this program is to help small systems comply with the new arsenic standard. So each dot on this map represents a demonstration site. And there are a number of types of different technologies being demonstrated, including absorptive media, iron removal, coagulation filtration, anion exchange, reverse osmosis, and point of use. And as you can see on the top of this map, iron removal is the second most frequently used technology being demonstrated at 14 of the 50 sites. And this slide shows the water quality of some of the iron removal sites, and all of these are groundwater supplies. The water is very reducing, as you can see, from the low dissolved oxygen and low redox potential, the ORP, as well as relatively high arsenic-3 and ferrous iron. The mass ratio of iron to arsenic the data is not showing here, but they are all greater than 20:1, meaning that there is a sufficient iron in the water to remove arsenic. So iron removal technology is a good technology for this type of water. However, the water also contains pretty high ammonia and TOC, so which makes the water treatment process a little bit more complicated. And my talk will focus on this site at Waynesville, Illinois, the one that I circled. And one of the reasons was because this site had the highest ammonia and TOC. You see the ammonia 3.8 milligram per liter as nitrogen, and TOC at 7.9 milligram per liter. So, and this Waynesville system was also the last iron removal systems that were installed under the demo program. So we were able to leverage our experience from the other sites, such as this Sauk Center in Minnesota, and I'll touch on that a bit later. So fast forward, I'd like to show you the arsenic compliance monitoring data that I downloaded from this website. That's the State of Illinois Drinking Water Program website. As you can see, before the arsenic removal systems was installed in July 2009, the monitoring data were collected from 2 wells, the well number 6 and well number 8. And then after the system was installed, the compliance monitoring was collected in the finished water, and it's showing as the green lines on this graph. And you can see the arsenic level went down pretty significantly to consistently below 5 microgram per liter. And also the sampling frequency was changed from the previous quarterly sampling to yearly sampling starting January 2015. And they also monitor total iron. That's on once every 3 years. So I only have this 2 pieces of data, the total iron, but they are all below 50 microgram per liter in the plant effluent monitored in 2012 and 2015. So the iron removal system seems to be doing pretty well in terms of removing arsenic and iron at this site. So next, I'm going to go into more details about this study. So the village of Waynesville, Illinois, has 452 residents with an average daily demand of 29,000 gallons. The water was supplied by those 2 wells with a combined flow rate of 84 gallons per minute. And prior to the installation of the treatment system, they only had a wellhead chemical addition, including chlorination, fluoridation, and polyphosphate addition. This next slide will just show, talk about some design considerations. The first is about what oxidant is good for this kind of water. So we all know that air is very effective for iron oxidation. That's why most of the plants use aeration. However, it's not effective for arsenic-3. And also because this water contains ammonia, so chlorine is not a good choice either, because chlorine reacts with ammonia to form chloramines, and chloramines are not effective for arsenic-3 oxidation either. So that kind of leaves, and also breakpoint chlorination is not practical because the chlorine dose will be very high. At this site, it could be as high as like 32 milligrams per liter. And also, that could lead to some DBP formation concerns because the water has very high TOC. So that left us with the permanganate. Permanganate can effectively oxidize arsenic-3 in the presence of ammonia and also minimize DBP formation. But permanganate has its own set of challenges, particularly with the dosing. If overdosing, then you know that you'll get pink water issue. And if underdosing, and then some arsenic-3 and iron-2 may not be completely oxidized. And also, because this water has very high TOC, and TOC would interfere with the manganese, with permanganate oxidation and filtration, it would exert additional demand for the oxidant. But there's no formula to estimate the demand by the TOC. And in our study, we also purposely avoided aeration to allow arsenic-3 and iron to be oxidized simultaneously for optimum removal. And we also kept the system pressurized to minimize the nitrification. So as I said earlier, we were able to leverage some of the experience from other sites. So I'd like to talk to you a little bit about this Sauk Center, Minnesota site, which had very similar water quality and also a similar iron removal system using the permanganate. We had some very interesting observations here and also learned quite a bit from this system. So as you can see on this graph, this blue line are the soluble manganese concentration measured after filtration. And the red triangle dots are represent the permanganate dose and to the y-axis on the right-hand side. So initially, the reason I put a quotation mark on the soluble because we collect the sample and filter them with 0.45 micron disc filters, and some colloidal manganese could pass through those filters and get into your filtrate. So that's why we call them soluble, quotation mark manganese. They're not true soluble manganese. Okay, so initially when we started the system, we add about 4 milligrams per liter permanganate. And we were able to oxidize arsenic. We got very good arsenic removal and iron removal. However, we noticed that the manganese, after filtration, the level actually went up. It was higher than what's in the raw water. So raw water had about 150 micrograms per liter manganese. So, intuitively we thought, oh, maybe we were overdosing the permanganate. So we lowered the dose from 4 to about 3 milligrams per liter. But surprisingly, you see the manganese concentration actually went up to almost 1,000 micrograms per liter. That's really contrary to our initial thinking. So then we started to as we further decrease the dose, and we were able to lower the manganese level. However, at the same time, we noticed that the arsenic 3 and iron-2 began to emerge in the filter effluent, so indicating underdosing. So at that time, we decided to do a jar test to determine what's the optimum dosage for permanganate. And I will show you the results of that jar test on my next slide. But just keep going. So based on the jar test, we decided to change the dose, to raise the dose to about 4.5 milligram per liter. And as you can see, once we raise the permanganate dose, the manganese concentration start to go down. And this one shows the jar test for the sock center water. And we actually did the jar test in the laboratory using the filter effluent collected from the plant and shipped to the lab. And because we wanted to determine this additional permanganate demand to overcome this TOC interference. And so this table shows that we added increment amount of permanganate into each of the 6 jars. And we mixed the solution for about 31 minutes, which represents the hydraulic, residence time from the chemical addition to the top of the filter. And at the end of the 31 minutes mixing, we measured the permanganate residual in each jar, and we also filtered the sample with the 0.2 micron disc filters. And then we measured that filtrate for arsenic, iron, and manganese. As you can see, the jar 1 is our control jar. We did not add any chemical to here. It has 5.5 microgram per liter arsenic to begin with, and the arsenic decreased a little bit, as you can see there. And for the iron, they're all below 25 microgram per liter, the detection limit. And the manganese level actually, decreased and also increased as when you see the jar 5 and 6. So we plotted the manganese data and on this graph. As you can see, we determined that the optimum dose for permanganate is between 1.5 and 2, and on both sides you either underdosing or you are overdosing. So, and each scenario you will have elevated soluble manganese in the finished water, and based on this optimum dose, we also figured out a empirical dose ratio. Basically, we used 1.5 or 1.6 divided by the TOC concentration of this water, which is about 4 milligram per liter, and we got this 0.4 milligram of permanganate per milligram of TOC. That's kind of the empirical ratio that we derived based on this water and this jar test. And then we were able to apply that value to our the Waynesville bench tests. So for the Waynesville bench test, it's a little different because we did the test before the system was installed to produce any water. So because we feel like, okay, we want to be more proactive this time, we want to do the jar test before we start up the system. So we actually use the bench test to determine the raw water oxidant demand and the proper dose to oxidize arsenic 3 and iron 2, and also to overcome the TOC interference. Another objective is to evaluate the potential for DBP formation. So, so we performed this test on site, and we used the fresh water from the well, and instead of using the 6-place jar test as we did for the sock center study, we used 1 liter amber glass bottles as a test apparatus because we try to avoid contact with air and try to preserve that condition. And we also determined the permanganate dose based on the stoichiometric amount. This 2.4 milligram per liter, that's based on the iron and manganese levels, plus the additional demand by the TOC. And we basically use 0.4, that empirical ratio, multiplied by 9 milligram per liter of TOC. And so we got 3.6, and add that 2.4, we got 6 milligram per liter. And we also included chlorine in this test, and we did some chlorine demand tests and figured out the dose will be 8 milligram per liter. So based on those conditions, we did the jar test, and we, as you can see on this slide, here we use 20 minutes as a reaction time, but for the sodium hypochlorite, we have 2 jars. The second jar is to give a more conservative conditions the purpose is for to look at the DVP formation. So we use 120 minutes instead of 20 minutes. And we also bump up the oxidant demand from 8 to 10 milligram per liter as chlorine. So at the end of the test, we measured the soluble arsenic. We did arsenic speciation, and we measured the metal content, and also the DVP in terms of TTHMs and HA5. So as you can see that the DVP formation was not an issue for any of these jars, and the permanganate definitely provides the best results for the arsenic-3 oxidation. And if you look at the chlorine bottle number 1 and number 2, we do have quite a bit of arsenic-3 still existing at the end of the test, indicating that, because remember this water has ammonia in it, so the chloramine, again, demonstrates that chloramine is not effective for arsenic-3 oxidation. So with that, I'm going to move on to talk about full-scale system performance evaluation study, and just very quick, some pictures for the building construction, and some pictures for the system delivery, offloading and installation. The design features, the system was designed at a 3.4 ppm per square foot, and it contained 4 vessels, 36-inch diameter by 72-inch tall, and each vessel contained 24-inch of GreensandPlus media, which is basically a silicon sand coated with manganese dioxide, and also a 12-inch of anthracite cap. The system was, each vessel was backwashed once every 3 days, consisting of 8 minutes of backwash followed by 2 minutes fast rinse initially, and later on we extended the time to 12 minutes of backwash and 4 minutes of fast rinse, and for more thorough backwashing. And each backwash would generate about 3,100 to 4,200 gallons of wastewater, and which was discharged to a septic tank on site. So this is a busy slide, but I just want to show you the sampling locations that we used during the performance evaluation study. So basically, we collected water from the inlet, and after the oxidant, after permanganate addition, and also after individual tank, as well as the combined tank effluent. And we collect the samples on a 4-week cycle. So for the first week of the cycle, we did the arsenic speciation, we did a lot more parameters, and the 3rd week of the cycle, we did just a total metal analysis. And we also collected the samples from the backwash and also in the distribution system, but I won't have time to talk about those results. So this shows the arsenic speciation data for the samples collected in the raw water, the after oxidation, and the treated water. So as you can see, the raw water, this pink color, the purple color represents arsenic-3, and the majority is arsenic-3. And at the after oxidation, this yellow color represents a particular arsenic. So this permanganate was very effective at oxidizing arsenic-3 and arsenic-5, arsenic-3 to arsenic-5, and arsenic-5 got absorbed onto the iron particles. And at the treatment, at the TT location, so the arsenic level went down to below 5 microgram per liter. So this graph just to show the total arsenic removal. We have a lot more data than the arsenic speciation. Again, this this yellow and pink curves represent the raw water and after oxidation, and the blue color represents the arsenic level in the effluent. So they're all consistently below 10 and actually below 5 most of the time. And for the iron removal, again, it's very effective. The blue line represents the effluent, and most of the time the iron was below detection of 25 microgram per liter, just with a few spikes here and there. I'm gonna just talk about conclusions real quick. So permanganate is very effective at oxidizing arsenic-3 and iron-2 in the presence of high TOC and high ammonia. TOC can interfere with the formation of filterable manganese dioxide particles and exert additional demand for permanganate. And it's critical to keep a pressurized system to ensure simultaneous oxidation of soluble arsenic-3 and iron-2 and prevent nitrification. And I purposely moved this manganese slide to my last one because, as you can see, although arsenic iron removal was very good, but for permanganate, for manganese, you can see that at the TT location, showing in the blue line, we were actually the level was higher than what's in the raw water. So they're actually most of the time they're above the SMCL. So the manganese may still require continuing attention. We could fine tune the chemical dose or do something else. And so with that, and I want to use this slide as a segue to Darren's talk about the biological treatment, where I think he had a very good removal on the manganese. So I just want to quickly acknowledge the operators of Waynesville, Illinois, my previous colleagues at Battelle, and also EPA ORD for the funding. Thank you very much. That's it.
Thank you very much, Lili. Anna, can you hear me?
I can, yes.
Okay, great. Thank you. Thank you, Lili, for that talk. And our next speaker, we'll go right into our second speaker. And as always, we handle the questions at the end of both speakers. So we'll tag team questions a little bit before the hour and then for the next half hour if you're able to hang on. Thank you again, Lili. And again, if everybody has missed the poll question at the beginning and you have more than one person in your room, please type that number into the question box, and then we can record it, and that helps us document how many people are attending the webinar and helps us justify these webinars. So with that, we'll go right to the second speaker, who is Dr. Darren Lytle. Darren is an environmental engineer for the US EPA's newly renamed Water Systems Division. Since joining the EPA in 1991, Dr. Lytle's primary goal has been to research drinking water quality. He has investigated and published works on drinking water systems, including work on distribution system corrosion control and water quality, such as red water control, lead and copper corrosion, also filtration for the removal of microbial contaminants, also biological water treatment, and iron and arsenic removal. So with that, I will hand it off. Dr. Lytle has a PhD from the University of Illinois. And I'll hand the podium off to Darren for his presentation.
All right. Thank you, Tom. So I'm going to go ahead and keep on going here. And as Lili said, I'm going to look at the removal of arsenic, iron, ammonia, and manganese by biological processes, so biological water treatment, taking a different approach to addressing the multiple contaminants. Before I start, though, I want to acknowledge a team of folks that have contributed. This has been a big effort, big pilot that we've performed over the last year or so. There's a number of EPA folks that have assisted here in the lab in setting up the pilot. And of course, the community has been involved, and their consulting engineer has been involved. They've been the ones, the small community has been operating the pilot and collecting samples for us, and that over the year period of time. And then lastly, some folks from AdEdge. The hope and intent here is that this pilot will lead to a full-scale system, and AdEdge is working closely with us and the community and the state to move forward with a full-scale design following the results of the pilot. So I'm going to present the pilot information, but before I do, I'm going to just get into some background information. And Lili covered a lot of the background nicely for me, but I'll go ahead and maybe skim through some of this more quickly now. But multiple contaminant groundwater sources are certainly an issue, and particularly for us in the Midwest, it is a large issue. And you know, as a result of source water characteristics, local geology, agricultural practices, and other things, we end up with these waters that sometimes have, you know, multiple contaminants that we have to deal with. And this can certainly complicate treatment. It can complicate the choice of treatment options or limit what options are available. You know, oftentimes, you know, one treatment approach typically does not address all the contaminants that sometimes we have to deal with in some of these source waters. As a result, we oftentimes have to utilize multiple treatment stages or processes to address all the contaminants of concern. And as a result, you know, there can be expensive costs associated with it, both capital and operational and maintenance costs. Complexity is always an issue too, you know, for a small system trying to treat a groundwater with multiple contaminants and a complicated treatment train, that can be an issue for the operator and for the community. And of course, we always need to think about residuals too. So multiple contaminants, multiple stages of treatment could result in different types of residuals with different characteristics that may be challenging to deal with. And you know, as it turns out, you know, a lot of the systems that have to deal with these, and I've already sort of suggested it, you know, are small systems. These small systems in rural parts of the country are oftentimes dealing with these complicated waters to address, and it just makes things all the more complicated and challenging. So the multiple contaminant scenario that we deal with, and you know, and I'm going to talk about, you know, 4 different contaminants in all of the same groundwater, but you know, any combination of these could be a challenge in itself. So you know, think of it, just don't think of what I'm going to talk about as an approach to deal with all 4, but you know, if you have 2 of these or 3 of these, you know, the approach that I'm going to discuss will address any combination. Ammonia, so you know, isn't, you know, of course, isn't regulated. And for those that have heard me talk over the years, I've been talking quite a bit about ammonia removal and biological treatment to address ammonia removal and why we're concerned about it. And again, it's not directly regulated, but certainly can be a big issue if it enters the distribution system, you know, creating nitrification issues, particularly if the concentration is over 1 milligram per liter, where that 1 milligram per liter of ammonia could go to 1 milligram per liter of nitrite as a result of distribution system nitrification, which of course is, you know, exceeds the nitrite standard of 1 milligram per liter. It can also impact treatment processes. In particular, arsenic removal can be impacted if there's ammonia in the water and you're trying to oxidize ammonia with something like chlorine, which gets tied up with ammonia and forms monochloramine, which is not going to be effective at oxidizing arsenic. So I'll talk about that in a second. Iron, we have a secondary MCL for iron, of course, of 0.3 milligrams per liter because of staining, aesthetic issues, staining of fixtures and faucets and clothes and other things. Red water, as we refer to it sometimes, and they may accumulate contaminants in the distribution system as well. So we want to treat iron and remove it from our water. Similarly, manganese has a secondary MCL of 0.05 milligrams per liter or 50 micrograms per liter for similar reasons as iron, you know, staining in brown water or black water issues. And lastly, arsenic, you know, of course, arsenic has a primary MCL of 0.01 milligrams per liter or 10 micrograms per liter. And of course, the health implications associated with arsenic are well known. So let's look at each contaminant just real briefly and quickly. You know, how do we deal with ammonia? Well, you know, monochloramine formation is an option, you know, but I would argue that it's difficult to manage because oftentimes ammonia varies in a source water, and maybe not so much in the source groundwater well itself, but what happens is many communities have multiple wells they draw from, and the wells have different amounts of ammonia, and they're oftentimes switching or rotating combinations of wells, and it can be a challenge to keep up with, you know, trying to tie up that ammonia without leaving much of a residual ammonia to go out into the distribution system. And of course, when it does go into the distribution system, it reacts with distribution system materials, corroding pipes and biofilm and everything else that it reacts with in the distribution system. It releases ammonia. So you have the ammonia out there, and that can still be an issue for you when it comes to nitrification problems. Breakpoint chlorination is certainly an option, but the concern there is particularly with some of the waters we're dealing with now, they have ammonia concentrations 2, 3, 4 milligrams per liter, that's a lot of chlorine to add. And then secondly, you raise the concerns of DBP issues. Biological treatment, of course, that's what I'm going to talk about and highlight that. And then there are others, ion exchange, RO, other chemical oxidation processes. I'm not going to, of course, touch on those, but they have concerns and issues of their own when treating ammonia. When it comes to iron and manganese treatment, of course, oftentimes when we have iron and manganese in the water, most of the time it's in the reduced 2+ oxidation states for each, and these are relatively soluble, indicative of the reducing source water qualities in groundwaters that we have in many parts of the country, as Lili mentioned. These reduced forms are relatively soluble, but can be removed by the reduced forms can be removed by some approaches, such as cation exchange, for example. But more commonly, at least in the Midwest, oxidation followed by filtration is the preferred treatment strategy. And again, as Lili mentioned, oxygen will be effective for oxidizing iron, but not oxidizing manganese. So if you have both in your system, you're going to be able to address the iron perhaps with oxygen or aeration, but not address the manganese. In the case of manganese and of course iron as well, you can use together. You can use strong oxidants like permanganate and ozone, or in the case of chlorine in combination with a manganese-coated media, these oxidants can get to the manganese, and in turn also get to oxidizing the iron as well. But again, I highlight biological treatment as a way of addressing the oxidation of each potentially. Lastly, arsenic treatment. So again, Lili covered this nicely, but look, when we have arsenic in the water, we need to, it's in a reduced form, which again, if you have reduced iron or reduced manganese or ammonia in your water, it's likely that it is going to be in the reduced arsenic-3 form. But the arsenic-3 form is very difficult to remove. And so we recognize that we have to oxidize it to the arsenic-5 state. And we can do that with strong oxidants like free chlorine, permanganate, and ozone. Now, where you get into trouble here is when you're trying to use free chlorine. Again, if you have ammonia, then ammonia gets tied up as monochloramine, or ties the chlorine up as monochloramine, and you're not going to be able to oxidize that arsenic-3 very effectively, as Lili has nicely shown. But once you oxidize it, then then the ability to remove it through iron coagulation or iron removal, through removal and absorption processes or anion exchange, we can remove the arsenic-5. That's that way. But of course, I highlight biological treatment is another option for us. And we've done work on arsenic oxidizing bacteria in the past and published some work on it. So there are bacteria certainly that are out there that can oxidize arsenic-3 to arsenic-5. And therefore, once in the arsenic-5 form, if there's iron around, you'll get removal through absorption of the arsenic-5 onto the iron particle surfaces, and then that is followed up with removal during filtration step. So the objective here is that I want to evaluate, and we're going to go through data here from a innovative biological treatment approach that we've talked about in the past for just ammonia removal. But look at it to apply it to removing all 4 contaminants from one groundwater source. That's removal of ammonia, arsenic, manganese, and iron from a groundwater in a system in Iowa over a year-long period of time. And I guess I'll bring up the difference here between the approach that I'm taking and what Lili has presented nicely is that her situation relies on the fact that oxygen is never introduced to the system. It never has been introduced to the system. And therefore she can, take advantage of the fact that the ammonia that's in that water is never going to be an issue. And it never has been in Waynesville. And because the ammonia goes out in the distribution system, and because the system's never been open in the past, there's never been enough oxygen, any oxygen, to address or oxidize the ammonia and have nitrification problems in that distribution system. So it's okay. So she can get by, and that system can get by with adding permanganate to oxidize the arsenic. Now, it would never work with chlorine because, again, the ammonia is still there because of the monochloramine formation issue. But she could apply permanganate to that system and oxidize the manganese and oxidize the arsenic and the iron with the permanganate, and not have to worry about the ammonia in the distribution system, because again, there's no oxygen for it to be oxidized by bacteria in the nitrification process. The situation I'm presenting is the opposite. These systems, and this is often the case, is they already have a treatment process in place. They're already using aeration for iron removal, but they're not getting the ammonia out of the system, and they're having nitrification problems, or they can't sufficiently oxidize the arsenic. They're not getting arsenic removal, so they're looking for another option. And I would never suggest, and nor would I ever suggest you suggest to anybody that has a system that has been aerating to go to an anaerobic situation, or remove or no longer aerate. The disturbance you would have to the distribution system would be, could be, catastrophic. You could have major upsets, to a distribution system that's been seen oxygen in air for many, many years, and then you want to maybe look at the approach to the Waynesville situation and no longer introduce aeration. And then at permanganate, that would be a disaster to the distribution system. So I throw that out there. Didn't want to forget that point, but you wouldn't want to reverse things. So once the system has been opened, we don't want to make it, we don't want to take the oxygen or air away from it. Okay, so the water, the source water. Here's a look at the source water. The community has 23 micrograms per liter of arsenic. It's arsenic 3 dominantly coming up out of the well. Iron is 2.9 milligrams per liter. Manganese is 0.08 milligrams per liter, or 80 micrograms per liter, and ammonia is 2.91 milligrams per liter. So this is a pretty challenging water here. A lot of contaminants of concern, as I've already mentioned. So the approach in the community this is a small community in Gilbert, Iowa, about a population of about 1,000. And the approach we're taking, and again, I've talked about this approach quite a bit on just addressing ammonia. And that's the idea of this two-stage, this aeration contactor, followed by kind of just a conventional dual granular media filtration system. And so really a lot of the work, the main part of the work is done in the aeration contactor. And really what that is simply an aerator. Air is introduced from the bottom through gravel. And the gravel serves to support biological activity, biological growth. And because bubbles continuously run up through this contactor as water is going up through it concurrently, or it can be opposite direction as well in terms of the flow of water and air, but we typically run it both the water and the air bubbled up from the bottom of the contactor concurrently together. What happens is that contactor is always saturated with oxygen, and so there are oxygen requirements, particularly with ammonia. When you have, for every milligram per liter of ammonia, it takes about 4.5 milligrams of oxygen to oxidize it biologically. And that doesn't even take into account, kinetic constraints and other things. And then on top of it, we have iron, which can be also oxidized by the oxygen coming up through this contactor idea, and then any other biological activity that may be important in manganese and arsenic oxidation. So the point is that, as oxygen is consumed by bacteria growing on the gravel, the biofilm never runs out of oxygen. And so it can do a lot of things throughout it. When you think of the traditional aeration followed by filtration system, what ends up happening there is you introduce the air, and then it goes onto the filters, and if they're biologically active, and ammonia is oxidized, and iron is oxidized. But what happens is you run out of oxygen because there's just not enough there. It runs out as the water goes through the filter because you're not replenishing it. And then what ends up happening is you don't get complete oxidation of anything, and particularly concerning is you form a lot of nitrite. So anyway, this is the approach that we take, and then of course the dual media filter that follows is there to remove the iron particles, the arsenic that are on the iron particles, and manganese as it passes through the contactor. The contactor is not intended to be a filter. It's porous. It's gravel, so it doesn't do much removal of particles. So that's what the approach is. The only chemical that we need to add is phosphate. We add some phosphate based upon past work. We've stuck with adding 0.3 milligrams per liter of orthophosphate to feed the nitrifying bacteria. This is just another look at the aeration contactor, just a series of them. But again, the point, I think I made the points pretty pretty clearly as to how this operates. You know, we don't expect to have to backwash an aeration contactor very often. In this system, we backwash once a month. But typically that, you know, because particles aren't building up, we don't have to do we don't build up head loss and things like that to warrant regular more frequent backwashing than that. So I'm going to jump right into some important water quality and operating parameters up front, and sort of change the order I gave this talk, similar talk a week ago, and I think the order needs to be changed from what I did before. And so I'm going to present this first because this is really the key to the operation of the system. And so I've got plotted here, first of all, the dissolved oxygen concentration in the raw water in the black here. And so the water coming up out of this well is typically, you know, 2 milligrams per liter or less. And then I've got the oxygen concentration in the contactor and then the filter that follows. And so I want to point out this period of time, the first 120 days or so. And you know, so when we started operating the system, the oxygen concentration we thought was, you know, was saturated and you know, and we were getting good, you know, good bubbles coming up through the contactor and all. But we realized that as we came up to 100 days, it sort of dropped off, and we realized that maybe we weren't truly saturated with respect to oxygen. And maybe we were having some constrictions in the contactor and the diffuser itself. So we turned up the volume of air, and sure enough, we were able to sort of, we'll say, clean it out a little bit and brought the oxygen concentration up closer to 10 milligrams per liter, where it remained in both the contactor and filter for the remainder of the study. Really important to get the oxygen concentration high. The other thing we changed, and unfortunately kind of changed it during the same period of time, was the loading rate. And loading rate is important because, of course, the bacteria need, you know, they need time to oxidize the contaminants of concern. So we started out at a loading rate of about you know, close to 3 gallons per minute per square foot at the beginning, but that historically was a bit higher than what we've done. We've piloted this in many locations in the past. We typically have operated more in the neighborhood of 2.2 gallons per minute per square foot. So we recognized that we were a little high to start in, so we brought the loading rate down to that 2.2 eventually as we approached 100 days of operation. So I wanted to just make the point that you know, during this first 100 days or so of operation, we were a little bit off on what we historically had operated under, and our oxygen was a little bit, you know, perhaps wasn't as saturated as it should have been, and we had some diffuser restriction limitations on oxygen. I also want to note here that at around day 250, there was a challenge that we wanted to evaluate what would happen if you doubled the loading rate. In other words, what happens if you have 2 contactors in place and one goes down, kind of thing. There was a redundancy question that was raised. So we turned, well, we basically simulated that by doubling the loading rate through the contactor during this short period of time. So we'll talk about that a little bit as we move on. And then lastly, the filters. The filters are operated, you know, at something lower than 2.2 gallons per minute per square foot. We used 1.8 gallons per minute per square foot, and that's kind of, you know, with the pilot, it's kind of difficult to control the flow rate going through the filters. And we did have some instances where we had the filters kind of went dry on us because, you know, if there's any disruption to the contactor flow, it affected the filters and they might run dry for a brief period of time. So we just, as a safety caution, to be safe, we operated at 1.8 gallons per minute per square foot, something a little bit lower again than the contactor. So let's start to look at some data. Well, yeah, I've got this bar on my computer, but that's okay. I can look up the screen. Okay, so let's look at the ammonium nitrite and nitrate concentrations from the contactor to start out. So the purple line here represents the ammonia concentration coming into the system, and then the black dots represent ammonia concentration through, in this case, this is the contactor, through the contactor. And so I guess the point here is that, you know, as I said, that first 120 days or so, we were modifying and adjusting some really important parameters, and it wasn't until we got things sorted out between the two, the loading rate and the oxygen concentration, then we see it, and then ammonia levels drop off rather nicely. And so they did around 120 days or so. It dropped off and sort of got to a minimum concentration of about between 0.5 and 1 milligram per liter. Not the entire, 3 milligrams per liter of ammonia that was in the water, but we did get down to between 0.5 and 0.1 once we were 0.5 and 1 milligram per liter once we got the operating conditions under control. During this time, we of course we see a little bit of nitrite peak, and we typically will see that because as things at the very beginning begin to happen and nitrification begins to start, you got to go to nitrite first. Nitrification is a two-step process. There's nitrite or ammonia oxidizing bacteria that take ammonia to nitrite, and then there's nitrite oxidizing bacteria that take nitrite to nitrate. So, you always see this spike because you got to first form the nitrite before the nitrite oxidizers can begin to function and operate. So we see a little bit of spike, not much, but then it goes away. And then during this time, the nitrate concentration comes up. And in the remainder of the study, as ammonia is converted, it's going straight to nitrate in the blue rather nicely. And then again, we have this test or challenge period where we double the loading rate. And when we do so, we see that the ammonia concentration comes back up and nitrate concentration goes down. So, again, loading rate is really, really important. And I've already alluded or mentioned this, that loading rate is important, and the bacteria just don't have enough time to oxidize the ammonia. And then once the loading rates change back, then the system goes back. Just a couple of operating parameters here. Again, I said the flow is co-current. The bed depth is 55 inches of half-inch diameter gravital. The airflow rate was 2.5 liters per minute. We backwashed the system monthly and operated it for 8 hours a day, 5 days per week. Okay, so let's look at the filter. So the filter, again, backs up the contactor. So what leaves the contactor goes onto the filter. And so you just see a continuation, basically, of continued biological activity in the filter. The filter, by the way, is full of 40 inches of media. The media is 10 inches of anthracite, over 30 inches of AdEdge's ADGS silica sand, which is a manganese-coated material, and it's backwashed every 24 hours of operation, or about every 3 days. And so what we see here is that, again, nitrite ammonia levels continue to improve as it comes through the contactor and leaves the filter. And again, until we get to that about 120 days, once we establish the loading rate and the oxygen concentration, once we get to that point, the ammonia levels are quite low, less than typically 0.1 milligrams per liter or more or less, up until the point where we have that period of time where we double the loading rate. When we double the loading rate, more ammonia is going onto the filter. And it can't take or handle it all, and so we see a spike of ammonia come out during that period of time. More evident in the filter is the nitrite concentrations, and again, because we have more surface area, I think, in the filter and more biological activity, that nitrite peak becomes bigger. It jumps up to just over 2 milligrams per liter, but then it drops off rather quickly. And again, it bounces around during the first 100 days or so, again, because the oxygen concentration is not where it needs to be, and the loading rate is a little more rapid than it needs to be coming out of the contactor. But once we get that established, the nitrite peak, we don't see nitrite concentrations above 0.2 or 0.3 milligrams per liter. Good thing about nitrite is it is oxidized by chlorine, so any little bit that's coming out is going to be oxidized by chlorine addition. As part of the disinfection, the community, would likely operate. So the filter does the job, takes care of the rest of what's coming in, with the exception of when we double the loading rate, then we have, a little bit of a degradation. The removal is somewhat impacted by it, but it comes right back once we change the loading rate back to the original loading rate. The loading rate, by the way, in the filters were not changed. It was just the contactor that were changed. We did add a second column, and because we wanted, my hope is always that we get all the removal of ammonia performed in the contactor. So a second column was added. This time, though, the column had 3 sample ports in it. Had a sample port at 25 inches. So imagine the water is flowing up from the bottom and the air is introduced from the bottom. At 25 inches into the bed, remember this is 55 inches of bed, of the total bed depth. there was a sample port, and there was another sample port at 37.5 inches above the bottom, and then at the very, very top, exiting the media was another sample port. And this is just looking at, time versus the concentration of in red, the ammonia, and in orange, the nitrite, and then nitrate in the yellow color. Again, here the difference is it's a bed is the media diameter. In this case, the media was 0.25 inches. So this is going to give us a lot more. This is going to more than double or approximately double our surface area in the contactor, giving us more area for the bacteria to grow on. And sure enough, what we saw is that at the top, well, at the bottom, I guess because it's co-current, but at the bottom, things take off the earliest, and by the time we get to 100 days, and again, this is about what we expect, about 100 days, because it typically, based upon our past experience, it takes about 30 days for complete nitrification to take place if a bed is operated 24/7. And given that we're operating, a fraction of it, it's just, a fraction of that, 8 hours a day, about a third, it takes about 3 times as much time to acclimate. That's what we expect anyways, and that's about where we're at. About 90 days is what we kind of expect, and we're about 100 days coming out of the top of this. And as we see, there's a lag of nitrification in the middle and at the top. So, but eventually, when we get to the end of the study and the operation, about 120 days or so, the majority of oxidation of ammonia is taking place in within the first, by 37.5 inches above the bottom of the contactor. So very effective. Reducing the gravel size has been very effective, and it's really, obviously, it's an important parameter. Increasing the surface area is an important parameter for the bacteria to grow and acclimate. Iron and manganese removal. Let's run through these fairly quickly here. Contactor 1 and 2, and then the filter. Iron manganese is iron concentrations coming in the black. One interesting thing is we found both in the case of iron and manganese that we actually had significant removals of both in the contactor, which never created a problem, or never created, resulted in a reported problem. We just backwashed it at a monthly rate, and that seemed to be fine, and never saw any problems with it. And so it did get removal, and then I guess the bottom line is that through the filter, iron levels were basically at the detection limit throughout, with the exception of a little blip during the time where we increased the loading rate. Similarly, manganese, again, same thing. We saw an enhanced removal of manganese in the contactor. It was disrupted during the increased loading rate, and it was also disrupted in the filter when we were operating under the lower oxygen concentrations and the higher loading rate in the contactor. So, like ammonia, oxygen is very important when it comes to manganese removal. But once we got through that period of time, manganese levels, with, again, the exception of one point here where a spike came up that corresponded to the iron spike, very good removals of manganese, typically below 5 micrograms per liter or so. So presumably this is all biological activity taking place and oxidizing the manganese in place in the filter and in the contactor. Arsenic removal. So this is looking at arsenic removal in the contactor and the filter. And again, we're seeing, again, if you remember, the arsenic concentrations in the raw water were about 23 micrograms per liter, largely arsenic-free. Coming out of the contactor, we're seeing a transition of arsenic from arsenic-3 to arsenic-5. And of course, some is being removed with the iron, so we don't have 23 coming out. We have a total of somewhere between 10 and 15 micrograms per liter coming out. But what's coming out is dominantly arsenic-5, so it's being converted as it comes out of the contactor. And then as we go through and look at what's coming out of the filter, it's all arsenic-5 coming out of the filter. This is all dissolved. This is not particulate. This is LCP, ICP-MS analysis, and it's focusing just on the dissolved form of arsenic. So again, we're getting removal, and it's being converted along the way of arsenic. Again, we attribute that to arsenic oxidizing bacteria, and then that arsenic being converted, as it's converted to arsenic-5, attaching to iron particles and being removed as iron is being removed. And then lastly, we're looking at total arsenic here, and this is contactor 1 and filter. We also have some contactor 2 data, but let's focus on contactor 1. and again, we see total arsenic. Now this includes arsenic 3, arsenic 5, particulate arsenic. This is done by ICP-AES. And again, we see removal of arsenic. This is the raw water in the black, and then what's coming out of the contactor. There's been a reduction, and then a further reduction as it comes out of the filter. And we do have a few points that are above the 10 microgram per liter standard. Not very many, but we went back and started to look at this, and we're going to need to take a closer look. But I think that there were a number of times when the system, the filters went dry, and we think that there may be some correlation with filters going dry and particulate removal of arsenic. But we need to look into it further. But for the most part, though, in the majority, over 80%, 85%, we're of the time we're removing arsenic levels below the MCL, and when it is above, it's just barely above. So we need to look a little bit more closely at that. But for the most part, good removal of arsenic as well. Last two slides, I just want to throw up alkalinity. Alkalinity, and the only reason I bring up alkalinity is because theoretically, the amount of alkalinity consumed is related to ammonia removal. The biology uses inorganic carbon for cell production and growth, and so theoretically 7.1 milligrams per liter of calcium carbonate is consumed per milligram of ammonia as nitrogen, and that's about exactly what we see. We've got 3 milligrams per liter or so of ammonia being removed, so that's about 21 milligrams per liter of alkalinity, and it's about roughly exactly what we see when we're at our ideal state between the filter and the finished water. So I want to just throw that up there. I always throw it up there because it's so amazingly on. Every study we've done, it's always right on. And lastly, HPCs, and I just say, hey, this is a biological treatment process, and there are going to be bacteria coming out of both the contactor and filter. And just for those that are interested in the biology of things, although it's not, certainly not we really want to do some molecular microbiology to understand what's going on in the system, and we're actually going to do that pretty soon. But we haven't got to it yet because of cost and things. But anyways, here's the microbiology of the system. So I'll wrap it up, because I know I'm running out of time here, and including that arsenic, iron, and manganese removal all have primary or secondary MCLs, and ammonia is not regulated, but I think you all understand the importance, significance of that. Aerobic biological treatment can be relatively simple, and I didn't get into how simple it really is, but it is very simple and reliable once you get things going. This system shut down, it's dried out, we shut it off for a week, it turns right back on again. Very reliably comes right back, removing the contaminants of concern. Media size, loading rate, nutrient addition, oxygen levels are very important and are very important in the design. It's robust and is viable and cost-effective treatment technology that can be suitable for small systems. And I think I'm going to wrap it up right there.
Okay, thank you very much, Dan. Thank you, Dan. Excellent talk, as was Lili. So now we're going to the question phase. But before we go, I know a number of you have to leave at the top of the hour. And I'd like to thank you for attending our webinar. And pay attention, because next September, we have September 26th, we have our next webinar. EPA funded 2 small systems research centers, university centers. And so that will be the topic. Their work will be discussed at the end of the last Tuesday of September. So please tune in for our next webinar series, and thank you so much for attending this month.